All right. Hey, everybody. Welcome to the Asia Pacific version of the weekly question show, where I'm going to answer your questions about space and or astronomy. And before we get too into this, I've got a prepared question that I've got from the audience, from the YouTube comments, and so I'm going to answer this question right now, just to just drop you right into the experience, or just get right into it. So this comes from Richie Bricker. Doesn't dark matter destroy real matter, and therefore we should stay the heck away from it? So, so this question is essentially saying, like, isn't dark matter antimatter? And so that if we got too close to dark matter, then it would annihilate and destroy all of our regular matter. And dark matter is not antimatter, or not that we know of. Dark matter is something separate. So antimatter is just like matter, except the charges are reversed. So, the opposite of the electron is the positron, and that there are antimatter particles for lots of the particles across the entire standard model of particle physics, and that if regular matter meets with antimatter, then they annihilate, and you get this perfect release of energy in the form of gamma radiation. Dark matter is not antimatter. Now, some amount, like dark matter could have anti-dark matter if we knew what dark matter was, which we don't. But, dark matter is, there's 5 times as much dark matter as there is regular matter. Like, we don't know what it is, but it accounts for 5 times as much matter in the universe. And so it would dominate. And it's around us all the time. Like, there is a dark matter halo around every galaxy in the universe. And so regular matter would be interacting with that dark matter, and if it was antimatter, then you would see the gamma radiation coming from all of this annihilation that was going on, and very quickly all of the regular matter would be gone, and you'd just be left with the antimatter. And like a question that we get from a lot of people is, one of the big weird mysteries about the universe is that there are equal amounts of matter and antimatter. So one of the questions that we get a lot is that there's this sort of big mystery in astronomy, is that back at the beginning of the universe, shortly after the Big Bang, there were almost equal amounts of matter and antimatter. There was like a slight difference between the two, a little bit more matter. And so the matter and the antimatter annihilated with each other, and you're left with this little remnant of matter. And so people ask, well, maybe the matter and the way you solve that problem is the matter and the antimatter aren't evenly distributed. So we happen to live in a place where there's a lot of matter, and maybe there's other places where there's a lot of antimatter. But the thing is that you would have these boundaries, these borders between the matter and the antimatter. And so when we looked out into the universe, we would see these places where the matter and the antimatter are rubbing up against each other and annihilating. And we would see floods of gamma radiation coming from those regions in space. And we don't see that. Now, there are a couple of places where we do see the gamma radiation coming from what appears to be antimatter annihilating with regular matter, but it's in very specific circumstances. Like, it seems to be coming from the center of the Milky Way, where maybe there's some interactions between the supermassive black hole at the heart of the Milky Way, or maybe it's actually kind of believe that pulsars might be the source of the antimatter, and so they're generating antimatter. The antimatter is finding matter, it's annihilating, and we're seeing the gamma radiation excess coming from the center of the Milky Way. But there's so much dark matter out there that if it really did annihilate with regular matter, then all the matter would be gone, and there would be 4 times as much dark matter, I guess, and then all of this energy. And it's it's a good thing that we don't have that. And so no, I mean, dark matter, whatever it is, does not interact with regular matter in any way that we can tell, except through its gravity. Okay. Okay, so let's move on to the regular questions. But before we do, Okay, so right, so just need to remind you guys that just the ground rules of this live stream question show. So the first thing is, I'm a journalist, not a scientist, and so I'm not able to provide any original new information about space and or astronomy. I can only report on the discoveries that the astronomers are making. Sorry. The next thing is I try to give emphasis to the people who have never had their questions answered before. And specifically that means like you haven't had your question make it all the way through into one of the question shows that we have edited and released here on the channel. So, if you're asking your questions here in the chat and we haven't posted it, then it still looks to me like you've had 0 questions answered. But if we have put your questions into our videos before, then I'll try to give emphasis to people who've never had a question answered before. And then the other thing is we get a lot of the same questions. So you'll get the same question over and over and over again, and we will try to sort of keep the questions novel and different. And so people won't know exactly what I'm going to say with every single question show because there's lots of new stuff. So, logic bug. I'm still upset that when I asked a real question, Fraser called me out for believing in unicorns. Obviously, I didn't explain my question correctly. So I'm assuming the question that you're asking was, if the universe is infinite, then can impossible things happen? I believe was the question that you asked, but if that's not the question you asked, then just let me know which was the question. I can clear up what my response was, because I promised that I wouldn't say that you believe in unicorns if you don't, unless you do. And if you do, then you do. Okay. Sorry, just continue to communicate with my wife. Okay. All right, let's get into the questions. Oops, where'd it go? Okay. Logic bug. What if the laws of physics are not uniform across the universe? So I guess this is the version of the question that you were asking. So the question that you're asking, like, could it be possible that the laws of physics are different in other places around the universe? And the answer is, of course. The assumption that astronomers make, and this actually goes back to Copernicus, there's this idea of the Copernican principle. And the gist of the Copernican principle is we're not special. That what we experience around us here on Earth, that we have a planet. The planet is held together by gravity, that there is temperature, that there are particle physics, that the forces that hold atoms together are the same. And wherever we have observed the universe, both locally and at the largest scales, the things that we see tend to be the same. That you can look out into the cosmos and you see other galaxies. So like our galaxy is not special. Those galaxies have stars, like our galaxy has stars. That those galaxies contain nebulae, and they have supernova, and you can go all the way back to the beginning of the universe and things seem to look roughly the same. And so, when there are weird anomalies, one very simple explanation is that the universe is not, that the laws of physics are not the same. And so like, why does the universe appear to be expanding due to the acceleration of dark energy? Well, it's easy to answer. The distant universe has different laws of physics out there. And so you can't look at the universe with the laws of physics that you understand. But the problem is then you literally can't know anything, right? Like there's no way to make any observations. There's no way to come to any conclusions about anything that you see if you can't trust in the bedrock ground that that what we experience in our portion of the universe is kind of the same everywhere that you go. That's the assumption that you have to make. Otherwise, you can't make any progress. And so, to the best of our ability so far, we have never seen any example that the laws of physics are running differently in some other part of the universe. And scientists have looked, like they have done a lot of interesting tests. They're looking for, say, do the fundamental laws of physics, the constants that underpin all of the various physics equations that they use, could those have changed over time? Could the force of gravity have changed over time? And these are the kinds of things you can actually make observations about. You can look at how gravity is holding galaxies together 10 billion years ago, and maybe the galaxies are holding together in a way that is different than the way that they are today. And then you could say, well, then it looks like gravity was weaker or stronger near the beginning of the universe, but we don't see that. And so, every single measurement that physicists and astronomers have ever made has held up to the idea that the universe isn't special, that our place in the universe isn't special. Flight Sim Dev. If the Big Bang is looking back in time, is there a possible way that it's not back in time, but rather we are looking into the future, like we are seeing where we are going? It would be very surprising if, when we look at the Big Bang, it is where we are going, because wherever we look out into space, we know that we're looking backwards in time. We know that light has a speed, that it is just shy of 300,000 kilometers per second. And so when we look at the moon, we are seeing the moon as it looked 1.3 seconds ago. When we look at the sun, we are seeing how it looked about 8 minutes ago. When we look at Alpha Centauri, we're seeing it as about 4.5 years ago. When we look at the center of the Milky Way galaxy, it's 27,000 years ago. When we look at Andromeda, it's a couple of million years ago. When we look at the cosmic microwave background radiation, it is 14.8 billion years ago. And the cosmic microwave background radiation is only 380,000 years after the Big Bang. And so it would be very strange. Like, what is the point? At what moment in the looking out into the universe are you no longer looking back in time? Like, we know it works locally. You look at Jupiter, we look at Mars. Mars is whatever. It can be 20 minutes ago, can be 10 minutes ago. We look at Jupiter, it can be an hour ago, or Saturn. And so, like, what point does this thing where when we look out, we look back in time, does it suddenly switch over to now we're looking into the future? And what does that even mean? So right now, all of the observations tell us that we are looking back in time, and all the observations that astronomers make hold together in this coherent, cohesive way. There's lots of outstanding questions still, but in general, you look out in space, you look back in time. Okay. Next one. Charles Orlando, has anyone seen the movie Moon starring Sam Rockwell? Good flick. I actually just watched it. So I am building a list of the top 100 science fiction movies of all time. And I've got my list, and I know I'm going to get a lot of people yelling at me because there's a lot of weird things on that list and things you might disagree with me, and notable exceptions, but that's how this works. But Moon is absolutely on that list. And so my wife and I just recently rewatched Moon. Totally holds up. One of one of the better science fiction movies ever made. Is it in my top 10? I don't think it's in my top 10, but it's definitely in my top 100. Chris Foam. Hey, Fraser, how come we started 2 hours late? Did we start 2 hours late? Is this not, did we not start on time? It's 10 o'clock. Did I set the time wrong? That's entirely possible. Avi's Gotten Flower. Haven't been to one of these in ages. What's with the hour? Did the polls finally shift? So I used to do the QA live streams every Monday at 5 p.m. Pacific. And I would get a lot of complaints from people in Europe saying, well, you do this thing at 5 in the afternoon, but then that's like 3 in the morning for us. And then people in Australia would say, well, it's 8 in the morning for us. And so we now rotate. So I will do one episode 5 p.m. Pacific time, and then the week after that, I'll do it 8 in the morning Pacific time, which is evening in Europe, but not like late night. And then we'll do it late night on Sunday for me, which is then morning for Europe and late afternoon for people in Japan and Australia and so on. So I'm trying to provide people with a show at their time. And there you go. You got it. You're Australian, right? So now you get a chance to watch one of the live streams. Okay. Next one. Man. Evo Love. Fraser, my imagination is terrified of the great attractor. Is this George Lemaitre's primeval atom vacuuming us back into the Big Bang? Okay. So there's a rant coming. Just prepare yourself emotionally. So there's something super weird about communicating concepts in space and astronomy that somehow our knowledge about what is the current state of space and astronomy research stopped with Cosmos. Carl Sagan, Cosmos, 1983. That was the last time anyone spoke about what's happening in space and astronomy. And then there has been nothing else since then. And I guess YouTubers are looking back to the things that Carl Sagan was pondering, and maybe a little before that, maybe back into the 60s and the 70s, and then turning these into videos about things like the Great Attractor. And the problem is that astronomy, and like, this isn't you, like, I'm not putting this on you, but there is this, man, like, we've been talking about this so much, and it blows my mind that, like, are we just not getting the information out very well? I don't understand. So, like, okay, so, and like, sorry, like, it's not your fault. Like, I just gotta say, like, you know, like, clearly you've been watching media that has been telling you about the Great Attractor and making you nervous about, like, what is it? What could it be? Right? We know that galaxies are sliding towards something that's on the far side of the Milky Way. And what is that thing that is attracting all of these galaxies? What is this thing in the universe that we know of that can cause things to move towards other things? Gravity. So, and now we live in the realm of infrared telescopes, which are able to look through the gas and dust that is blocked by the center of the Milky Way. And so now astronomers have mapped out the thing that is the great attractor, and it is galaxies. That there are galaxies on the far side. There are more galaxies on the far side of the Milky Way. There's a bigger concentration of galaxies on the far side of the Milky Way. And because there is more mass concentrated that just happens to, like, coincidentally happens to be on the far side of the Milky Way, then galaxies are kind of sliding generally in that direction. But they're actually also just expanding. Like, everywhere we look, galaxies are moving away from us. And really only within about 5 million light years of us do we stand a chance of eventually merging into a larger group of galaxies or into a giant elliptical galaxy. And so thanks to infrared telescopes, we can map out these galaxies that are on the far side of the Milky Way. It's kind of amazing how much of this giant group of galaxies is on the other side of the Milky Way that they've mapped out. And there's very little mystery left about this. There's probably still a few hundred galaxies that they haven't found yet, but they've found so many of them. And as new and better infrared telescopes come along, they map out more and more, and they find more, and we report on them all the time. So it is interesting to me. And like it's like a meme thing. It's a cultural thing, like that these things echo on YouTube for clicks. I don't know. It's weird because I feel like we've been talking about it, and I don't mind explaining it. Like, the great attractor is a really cool thing, and I love to talk about it. Right? I don't mind. It's fine, but I just wonder why the information isn't getting out there. The counter to, we don't know what it is. Could it be a vacuum cleaner that's sucking up galaxies? Right? We know what it is. It's just gravity. Anyway, so yeah, it's so weird. It's just so weird to me. Again, Evo, totally not on you. It's on the people who are not doing their homework or not staying up to date as they're describing things in the current state of astronomy as we know them. Right? It would be like talking about football and wondering and talking about the state of the game as it was in the 1980s, and not noticing that new Super Bowls are being won every year or something. I don't know. Okay. Gonna be 2MS. Will LSST have regular data releases, or will we be in an attic-like state waiting for science data like the bulk of Gaia data isn't out yet? So the good news with LSST is that the data is going to be live. So there is a brief delay as the telescope is pulling down its live data, and then because it has to go from Chile to the US, where the Department of Energy removes surveillance satellites from the images taken by Rubin. And then this information is in a live feed. And so as close to real time as humanly possible. And so what's going to happen then is because, Rubin is looking for events that are sort of very short nature, right? You're looking for supernova, you're looking for asteroids moving, you're looking for Planet 9, you're looking for comets, you're looking for weird transient events. And a lot of the times, the faster you notice the supernova, the quicker you can turn telescopes on it and do follow-on observations. And so there won't be these big, long data releases. I mean, there will, but it'll be different because the way Rubin works, and we got sort of a nice glimpse of this earlier on this summer, is that it's going to come back and image each spot in the sky dozens of times throughout the course of its 10 years of operation. And normally with a telescope, you will say do observations of a specific spot in the sky. You'll image the spot in the sky, and you'll do an exposure, and then you'll do another exposure, and then you'll do another exposure, and each time you do another exposure, your data gets better and better. You get more data, less noise. The image gets clear. The galaxies pop out, and you have however long you're doing your exposure to kind of make the observations that you want to do. With Rubin, it comes back every few days and takes another image. And then astronomers will be able to stack up those images to be able to look for things that have changed in those images, in addition to just really deep, high quality images taken, over the course of 10 years. Like, you can get really beautiful, high quality images over time, building up one exposure at a time. But there will be ways to just dip your mind into the river of information that is flowing out of Vera Rubin, and just like, oh, supernova, oh, asteroid, and watch these events. So they're building in filters that will identify the kinds of events that astronomers are looking for. They're building a pipeline, and then all of those data will be dumped into these gigantic hard drives, and astronomers will be able to go through those hard drives, or be able to run database queries on all of those data and look for the kinds of things they're looking for. So they can say, well, this region of the sky, show me all the supernova that went off from this time to that time, and they'll be able to pull up all of these queries. So you're going to kind of get the best of all the worlds, right? You're going to get something that's going to feel like real time, like you're watching a stock ticker, like you're watching a live event. You're going to be able to go through all of the data as quickly as it is made available. Just boom, because it doesn't need, they're sort of doing all of the processing and rendering and pipeline immediately. And then there's going to be data releases as they're doing these big long exposures and releasing interesting information about the structure of dark matter, weak gravitational lensing, baryon acoustic oscillations, surveys of galaxies, things like that. There's going to be a ton of data releases on top of that. So yeah, it's going to be the best of all worlds. And I don't know when it starts, which I know is always the question. But I am still incredibly excited for it. Hangman 747 Tin Man. I was watching your Magnetar interview. Could we look at the neutron to neutron star merger witnessed by LIGO and see if it became a magnetar? Well, that's the question. So in that interview, Dr. Genevieve Schroeder was saying that she was saying that what they were looking for was that there should be some kind of radio signal coming from whatever is left behind after the two neutron stars merged. And a certain kind of radio signature would tell you that there could be a magnetar as the remnant. They didn't see a remnant. They didn't see that radio signal. Now, it could just be that it turned into a heavier neutron star. It could just be that it turned into a black hole. Could be that it just vaporized entirely and there is no remnant behind. But they got a null result on is it giving off this signal that would tell us that it is probably a magnetar. But I think what you're asking is like, would you see the presence of a magnetar in the collision after the two neutron stars merged? And the problem is that you need to have mass that is moving for it to be able to give off gravitational waves. So while the neutron stars are spiraling around each other, getting closer and closer and closer, then you've got a ton of mass that is whipping around, and you've got these gravitational waves that are emanating outward. Once they merge, then they turn into a black hole or a magnetar, or they vaporize. And now there is no longer moving mass. And so you can no longer detect the gravitational waves coming from it. If you see like the animations of these things, you see the neutron stars with the black holes going around each other, and you're seeing these gravitational waves that are going out, and then they merge into a thing, and then the gravitational waves are gone. Because now it is no longer this thing that's wobbling, it's no longer something with many times the mass of the sun wobbling around hundreds of times a second. It is just sitting there out in space. So unfortunately, LIGO can't help you find the remnant. Now I say that, but astronomers are very clever. And so I'm sure they're like, no, we think we've got a way. One idea is like you could potentially find lopsided supernova, where when the supernova goes off, even though it's just one star, it maybe doesn't explode as a perfect sphere. It blows off one side of the supernova first, and then that causes the rest of the star to jet off in the opposite direction. Now you've got gravitational waves. Maybe you could detect this. So maybe if two neutron stars merge together, then it's lopsided in some way, and it's kind of like wobbling around in this lopsided way, and then you would get some gravitational waves coming from it. So, but if it does form this sort of perfect sphere afterwards, then you wouldn't be able to detect it in gravitational waves. Okay. Brent Calloway, are there any missions being planned to explore lava tubes on the moon? So there are no current official plans to send any mission to any lava tubes on the moon, but we've reported on a ton of ideas where people have proposed them. There was like some NIAC grants that had been awarded for thinking about exploring lava tubes on the moon. There was a recent one that we reported on. I did an interview on the channel with her. I forget her name, but the idea would be to land right at the edge of a lava tube and be able to sort of do scans inside the lava tube, try and map out the interior of it to some degree. People have proposed robots that can be sort of lowered down on a cable down into the lava tube, down to the bottom, as well as robots that could be dropped down, and then they could have a propulsion system on board so they could land down at the bottom of the lava tube. The other thing that's really interesting is that many of these lava tubes are thought to exit. So back when it was a river of lava going across the surface of the moon, then the lava would have flowed out and emptied out the chamber, right? That's why you get the lava tube, and it actually would have gone out onto like a plane at the other end of the lava tube. And so you would have this giant cave entrance. And so instead of having to like go down into the lava tube through the skylight, you could theoretically just drive in the exit point on the lava tube. So, but right now, no, there's no official mission, not from ESA, not from NASA, not from the Japanese Space Agency. No one is currently building or sending a mission to explore a lava tube that I am aware of. Karen Deepgill. How does the mass of the Milky Way galaxy's supermassive black hole compare to the mass of other galaxies in the universe or to nearby galaxies? So the mass of the supermassive black hole compared to the mass of the rest of the Milky Way is about 0.1%. So less than 1% of the mass of the the Milky Way is the supermassive black hole at the heart. It has like 4.1 million times the mass of the sun. And the Milky Way has a lot of mass in it. It's thought to be 100 billion stars. I forget the exact mass, but it's like a trillion, 1.5 trillion solar masses, something like that. And so, people always think that, the supermassive black hole is like a big chunk of the mass of the Milky Way, but it really isn't. And that is fairly normal for galaxies in our epoch. So the galaxies we see around us, they have supermassive black holes that are kind of roughly that same ratio of black hole to galaxy. And those numbers can go up and those numbers can go lower. But a trend that is seen is as you get earlier and earlier into the universe, the ratio of the black hole goes up. And so you'll see galaxies with 1% the mass of their galaxy. You'll see, black holes that are 2% the mass of the galaxy. And early on in the universe, the kinds of galaxies that you're seeing, say, with James Webb, where they're just a few 100 million years after the Big Bang, the galaxies, like maybe 10% of the galaxy is the supermassive black hole. And one of the big outstanding questions that astronomers have is, what comes first, the supermassive black hole in the galaxy or the galaxy around it? And the traditional model, the kind of lambda cold dark model, the lambda cold dark matter model of the universe really kind of relies on this bottom up formation of galaxies, that you have these smaller proto galaxies finding each other, merging together, their black holes find one another, merge into a more massive black hole, and the thing gets bigger and bigger and bigger over time, and that the mass of the black hole remains in pace with the mass of the galaxy and all the material that's accreting around it. But if the galaxies have supermassive black holes that are much, much heavier than anticipated, then this could be more evidence that you're getting these direct collapse black holes, that instead of you having to go through this, you start with a little black hole, like a stellar mass black hole, and then two stellar mass black holes merge, and then more black holes merge, and eventually, and the black holes are feeding, and you work your way up to these bigger massive black holes. Well, maybe you have the direct collapse method, so you just have giant clouds of gas and dust that collapse directly into black holes with no intervening stage. And so that would give you an overly massive black hole compared to the galaxy around it. But this is all the fresh stuff, right? Like these are the weird mysteries that astronomers are currently working their way through. Okay, next one. Martian. Oh, I see. Someone was asking about my movie list. The Martian is in my top 10 sci-fi movies. But my idea of a sci-fi movie is fairly broad, so I include The Princess Bride. Is that sci-fi? I mean, it's fantasy, right? I include Bill and Ted's Excellent Adventure, which my wife is not sure that qualifies for science fiction, but I think it does. Curtis Horn, what do you think of the video Dark Matter is Not a Theory by Angela Collier? I think that video by Angela Collier is one of the most I'm trying to think of the word here. It was one of the most paradigm shifting videos I think I've ever watched on YouTube. I think that video from Angela is probably one of the most important videos that I've ever watched, and has deeply changed the way I discuss and describe dark matter, dark energy, and really anything that is a collection of observations. And, if you haven't watched the video, you absolutely should, because she is tackling head on this really low energy attitude response that a lot of science communicators and scientists get from people who don't understand the search for dark matter and the search for dark energy and just a lot of what astronomers do in general. And it's great because like it's like the perfect clickbaitiest title ever, where because she's saying dark matter is not a theory. And so someone who thinks like, yeah, dark matter is just this dumb thing, like scientists are just making this up and it's not a theory, and finally a physicist is admitting this lie. And what she says is that it's not a theory, it's a series of observations that what astronomers call dark matter is actually a large collection of individual, independent, well-performed, very accurate observations that tell us that there is some additional effect in the universe that we don't understand, that there is this disconnect between what the theories say, our understanding of gravity, and what we perceive out in the universe. And then people have tried to come up with ideas to explain how this works. And so in that video, she goes through the different methods that astronomers use to detect the presence of dark matter. And that some of these you could do with a small telescope. Like if you were willing to put in the time and you understood the science, then you could replicate the results. Nature is giving you the answer, right? Nature is saying, here's the thing that you thought you understood, but you don't understand it. Go ahead, prove it yourself. Great. And she goes through all of the lines, the independent lines of evidence that tell you that there is something there, that this mystery is real. Now, we don't know what the answer to the mystery is, but that's fine, right? Like that's not new, that there is a mystery and we don't know the answer to the mystery. That's how science works, right? That you uncover something new and unusual and then you have to work out what the answer is. And the analogy that I love to use is, that you're driving in your car and your car starts making a funny sound, right? You have made an observation. You know what your car is supposed to sound like, and now you've detected something new, an observation. And you are driving in the car with a friend and you ask your friend, you say, hey, do you hear that sound? And your friend goes, yes, I hear that sound. Okay, you have an independent party that has confirmed your observation, right? You now have, that is science. You make an observation, somebody with the same scientific equipment, in this case, a set of ears, makes the same observation. You're not a crazy person. Okay, great. Car's making a funny sound. Shouldn't be making the sound. You take it to a mechanic. So now you're trying to figure out why the car is making the funny sound. But no one argues that the car is making a funny sound, right? This is dark matter. No one argues that the universe is doing things that nobody anticipated, nobody expected, that galaxies are rotating too quickly, stars are moving too, are not orbiting in the way that you would expect. You're seeing invisible regions or blobs that are warping and distorting space-time. You can measure the effects in the cosmic microwave background radiation. These observations are real. And anyone who is willing to invest the time will understand those observations are real. And the fastest way to show that you don't know anything about it is to go, well, this isn't real. Physicists are just making stuff up to get a paycheck or whatever, right? Like, oh, great. Tell me you don't understand without telling me you don't understand. And so, back to the car analogy, you take your car to the mechanic. The mechanic says, yeah, I don't know what it is, but let's start with the wheel. Right? Like maybe one of the wheels is loose or whatever. And so then they pull off all the wheels, they check, put it all back, put a different set of wheels. Car's still making the same sound. Okay, it wasn't the wheels, right? You had theory. And so in that case, maybe that is, well, maybe gravity doesn't work the way we think it does at the largest scales, right? Let's change the tires and see if that works. Nope. Still getting the same sound. Nope. New definition of gravity doesn't explain all of the observations made for dark matter. Okay, great. So then you keep going and say, okay, maybe it's transmission. Fix the transmission, still making the sound. So like that is the physicist saying, well, maybe it's neutrinos, right? That's a thing that we know. The neutrinos move that, close to the speed of light. They don't interact with regular matter. We know there's enormous amounts of this. Like there are hundreds of millions of neutrinos passing through your body every second, and hundreds of billions. Anyway, you don't even feel them, right? Because they don't interact with your body in any way. But they're real, and we know they're there. So maybe neutrinos could explain it. Well, no, the problem is that neutrinos are too hot. They move too fast, that you wouldn't get the clumping that you do with the gravitational lensing the way you do with, if you had neutrinos. So it has to be something that's cold, something that's moving slowly. Okay? Back to your car analogy, you try another thing, right? And so we don't know what dark matter is, but the range of things that could explain the observations that have been made are sort of the running out of places to hide, right? It's got to explain all of these separate independent observations. It's got a lot of work to do. Whatever the theory is, it's got to be able to solve that. And we're down to really that there's some massive particle, slow moving, cold, massive particle that doesn't interact with regular matter or with itself, but it does, produce gravity. Some versions of modified gravity, but that doesn't explain all the kinds of observations. And maybe primordial black holes or black holes of different masses can still explain it. It hasn't been totally ruled out, or some combination of a bunch of different potential particles. So that is, and what's great, because you go back to Angela's video and you watch the comments, and the comments are just like not getting it, right? Like they literally just didn't listen to what she said. And either we're like, yeah, you're right, Angela, it's a dumb theory, it's not real. Or you don't understand, you dumb physicist lady. I have thought this through and have a general skepticism and pessimism for the scientific establishment. And therefore, I think this is another scam that is unleashed upon the regular world and the people who pay the salaries of these scientists who are just trying to scam us. You dumb lady. And, so it was amazing that you just follow on video where she just like patiently went through it again, but it just won't stick. So I think we kind of get to this place where we've done all we can as explainers. And so either you're off the train at this point. You're just like, you not only don't understand the state of the science and the astronomy, and you kind of don't want to, like, you just don't, like, you're not interested, and that's fine, right? It's not like the search for dark matter is going to cause you any personal issue, right? And that's great, but also stop obsessing about it. Like, why are you so obsessed about it? Like, why does it bother you so much that this thing that you don't understand and haven't taken the time to understand, but you're sure is wrong? When if you're willing to take the journey and understand the actual nature, actual thing that astronomers understand, then you would probably be amazed and impressed and in awe and wonder at the fascinating mystery that nature, that the universe has laid out in front of us, that is going to keep people puzzling and busy for a while. And for the scientific community, they've got a range of really cool new toys that have shown up to help them get to the bottom of this mystery. So you've got, obviously, there's the DESI survey, which we reported on last week. There's there's Nancy Grace Roman, there's Vera Rubin, there's the Euclid mission, there's James Webb. So there's a lot of great tools that have come online in just the last couple of years and or are coming in the next couple of years that are going to make it even harder for dark matter to hide. There are tons of experiments here on Earth, tabletop experiments in mines, in different countries, particle accelerators. People are trying to make dark matter in the lab, trying to rule out what dark matter might or might not be. And the progress is really exciting. And with this new range of tools, we should get an answer, right? So hopefully, and if not, then it's an even trickier problem, but the observations remain. So yeah, if you haven't already watched it, definitely watch her video. And again, like one of the most powerful videos, I'm going to say one of the most powerful science explaining videos I've ever watched. Good job, Angela. You crushed it. Odin Reactor, Fraser, don't be calling people stupid when you're just a communicator with no scientific or academic credentials to your name. Tone it down. No, I'm not saying they're stupid. I'm saying they're calling Angela stupid. So just be clear that in the comments, if you read the comments on Angela's video, there are tons of people, and the gist of their statement is, "Hey, stupid lady, you're wrong. You're super wrong about this thing that you have studied for decades." Okay. Whew. Burned up a lot of time on that one. Apologies. 1,000 dots. You have often said that you expect us to be alone in the universe. Do you mean only in terms of intelligent technological life? I've always thought that simple life might be everywhere. Again, this is my opinion. This is not a scientific theory. I have not, this is purely a philosophical answer that I have come to, leading off of what, the Fermi paradox says, which is that life should be everywhere, but we don't see it. So where is everybody? And the crux of the argument is that advanced civilizations will travel to other star systems. Like, will we ever be able to travel to other star systems? Then other civilizations should be able to do the same. And so why don't we see their spaceships here in the solar system, right? That's the crux of the argument. And I don't want to re-debate the whole thing, but where I go deeper on this is that, how do you get an advanced civilization? You have a civilization that is capable of tool use and certain levels of intelligence. How do you get a civilization that's capable or how do you get a being that has tool use? Well, it evolves from a being that wasn't able to do tools. And where did that come from? It came from a multicellular organism. Where did that come from? Probably from a single cell organism. As you just chase that all the way back down. And so, intelligence is an extremely powerful evolutionary adaptation. And we've seen intelligence evolve many times here on Earth, not to the point that they're sending rockets to the moon, but you've got birds, you've got octopuses, you've got elephants, you've got lots of animals that are varying levels of intelligence. And so, like, in a million years, would the elephants evolve more intelligence? Would the parrots evolve more intelligence? Would the octopuses? Like, what would it take? 1 billion years? Who knows? And so it feels, because we see this convergent evolution, we see this advantage of intelligence evolving many times, then it appears that it's kind of inevitable that as soon as you get life on a planet, you start to get this this Darwinian evolution that eventually brings you to some life form gaining intelligence and using that to exploit their environment better than their competitors. And then that intelligence is this ratchet that just keeps you going. And so you kind of have to follow this philosophical argument all the way to the beginning, which is that if we don't see any life out there, then there was no precursor life that was able to evolve to that intelligent life. Therefore, my personal philosophical opinion, which is not backed with observation, is that the reason that we don't see aliens anywhere is because it hasn't evolved anywhere. Like literally not bacteria, because bacteria gets you rocket ships. Caswer, are there things that spin fast enough to have real relativity weirdness happening? Absolutely. And the thing that spins very quickly are black holes. So most black holes are spinning very close to the limit of what is predicted by relativity, that they're going about 70% the speed of light. That if you were standing on the surface of the black hole, which I do not recommend, then you would be, the path that you're following around the black hole is going up to about 70% of the speed of light. And then beyond that, it's sort of like it just takes ever more mass and faster spin to get you going faster and faster. And so that's the kind of practical limit for how fast black holes can spin. And the surprising thing is that most of them are spinning at that rate. That there are examples of ones that aren't quite spinning that quickly, but whenever astronomers are able to accurately measure the spin rate of a black hole, it is approaching the maximum rate, and that that black holes consume so much material, stars, planets, but mostly gas and dust, and that gas and dust falls into the accretion disk around the black hole and is spinning around the black hole, and then it falls into the black hole and adds to the spin of the black hole, unless the black hole is spinning in the opposite direction of its accretion disk. But in general, these black holes are spinning very, very quickly. So when you ask about kind of like relativity weirdness, well, the problem is the black holes are already experiencing relativity weirdness because of their intense mass. If you remember the movie Interstellar, where clocks tick more slowly when you are in the presence of a very heavy mass. And so they went down onto that planet in Interstellar, they came back up, and then it had been 30 years or whatever. And so you're getting that relativity from the mass. And then theoretically, if you're on the surface of the black hole, again, not recommended, then you're going to experience the time dilation from your moving at 70% the speed of light. Save the planet. I see the scopes are back. Any you had to be there moments during your observation time? What were your favorite views from the Daub, and what eyepieces and focal ratios were involved? So we had 10 days of pretty clear weather there, and so I was able to get the telescopes out every night and observe both the big Daub as well as the various smart scopes. And I got the new smart scope. You can see it there, the Dwarf Mini, which I took a couple of pictures with, and then the clouds roll. Yeah, I get the new telescope, and then the clouds roll in. Of course, right? Classic. But it was bad seeing. So, what I was really excited was to be able to see the bands and hopefully see the great red spot on Jupiter, because Jupiter's really high and bright right now. And so every night there was Jupiter. I pulled out the telescope, and then it was just a murky mess. And only one time on those 10 nights was I able to actually look at Jupiter and be able to see the bands on the planet. Um, so I've got a bunch of eyepieces. I've got some really nice 2-inch eyepieces. I've got like a really big like teleview eyepiece that is a very wide field of view, but it's just so nice to look through the glass because the I don't know the glass is like, or the optics on the eyepiece are like this big, so it's just this huge piece of glass that you're looking at, while the more higher magnification eyepieces are these just teeny tiny little pinholes that you look through, 5 millimeters, things like that. And then I've got a zooming eyepiece, so you can sort of switches between two ratios, but I don't know what the focal ratio is on the telescope. I haven't actually sort of done the math on it, but I've got a 5 millimeter eyepiece with a Barlow lens, which makes Jupiter take up like a big chunk of the sort of seeing area. And then I've got this, like I said, I feel like it's a 45 millimeter. It's like really big. And so Jupiter's this tiny little dot, and you can't even make out the bands on the, on the planet and the moons. Like it's as if I was looking through my binoculars, but it has a very wide field of view. And so I can look at the Orion Nebula or the Andromeda Galaxy in it, and it looks really cool. Gabrielle Server. Hi from Spain, Fraser. What kind of equipment do you think is worthy of observing the solar eclipse in August? First, congratulations if you're going to get a crack at seeing the eclipse in August. It's going to be a tricky one. So with the eclipse that we did 2 years ago in the US, it did a big swath of the US, Mexico, US, and up into Canada. And so I watched it from Dallas, and it was a great view of the, we happened to be right on the pathway of the eclipse. But for the one in August, it goes through a little bit of Iceland, and then it goes down this little sliver of land, sort of in northern Spain. And so everybody is going to be trying to pack into this teeny tiny area of Spain. It's going to be a gong show. So if you live very close to it, good luck. So what kind of equipment? What's the standard equipment for looking at eclipses? In general, you don't need anything. When I watched the eclipse, I got a pair of eclipse glasses. So they're the Mylar lensed glasses that you can wear, that you can look at the sun safely through the glasses. And then once the sun is completely covered by the moon, then you can take off your glasses. You can just watch the eclipse with your eyes. And it's so amazing. Like I totally get why people become eclipse chasers, and they then chase eclipses around the world, trying to catch up on that experience that they had with that one. So it's totally worth it. But you got to see totality. Like whatever you do, make sure you get to totality. That 100% is a completely different experience from 99%, and don't let anybody tell you differently. Like if you're planning on going and seeing this eclipse, and your family's, or your spouse, your friends, whatever, your parents are like, no, we can see it kind of from here, it's going to be 75%. That's pretty good. No, it's not. It's not the same. It doesn't count. It's got to be 100%. That's when it gets crazy. And that's it. That's all you need. Now, if you've never seen an eclipse before, I do not recommend doing anything else than a pair of eclipse glasses. Buy them now, and your eyeballs, right? Take off the eclipse glasses when you're at full totality. Just enjoy the show. Because you can get a telescope, you can get a camera, you can try to take pictures of it. But it's now you're not enjoying the eclipse. You are trying to capture the eclipse and you miss it. So it's a very tricky observation to make because the brightness changes very rapidly. It goes from full sun, which is going to require one camera setup, to darkness, very faint object, requires a totally different camera setup, and you've got to be able to run through all of those camera settings step by step by step. If you want to use a telescope, you need to get a solar filter on the front of your telescope so that you can be able to observe the sun and watch as it's getting chomped out by the moon. But once it wraps up, then you don't see anything in the telescope because it's just too faint. So, and you've got the solar filter in front of your telescope, so you have to look with your eyes. So yeah, my recommendation is no gear beyond, ANSI certified set of eclipse glasses. Michael Young, any update on the pressurized lunar rover that Toyota was working on? Not that I've heard. I think they've partnered with NASA, or had partnered with NASA, that it was going to be in the kind of Artemis 6 or 7 range that they would be sending the rover to the surface of the moon, but I haven't heard any updates. And like right now, everything is up in the air with Artemis. Pardon the pun. Canadian Space Advocate. Next Sunday, the Superb Owl Olympics and Artemis 2. Which one will get the most views? Probably the Superb Owl. Damien Reloaded. Do you know of any caves on the moon? Yeah, we see examples of dozens of caves on the moon. The skylights of the collapsed roofs of lunar craters. Of lunar. We can see dozens of skylights on the moon. These are the collapsed roofs of lava tubes on the moon. And there's some really interesting images that have been taken of these skylights where you can see in some cases, I think the ones on Mars, you can actually see the floor below, taken from orbit. But yeah, there are many of these skylights on the moon. Potato Biden, is the southern hemisphere more hazardous than the northern because it is more facing towards the center of the galaxy? No. There's nothing special coming from the center of the galaxy. The source of radiation is the sun. The solar radiation comes from the sun, and then cosmic rays, galactic cosmic rays, and they come from all directions. So they're not coming preferentially from the center of the Milky Way. And the southern hemisphere isn't facing towards the galaxy in any specific way. Where I live in Canada, the Milky Way heads straight overhead. The center of the Milky Way is fairly low on the horizon for me, and if you're in Australia, the center of the Milky Way is much higher in the sky. But then as you move even further south, then potentially the center of the Milky Way is going to be low in the sky. Rodney Allen, Lagrange point question. How were these discovered, mathematically or observationally? So, So they were discovered mathematically. Let's see here. Just want to make sure I get his name right. I can't believe I forgot his name. Joseph Lagrange. Yeah, okay. All right. Yeah, so the Lagrange points were predicted mathematically by Joseph Lagrange. And back in like the 1700s, he did the calculations that there should be these gravitational stability points in the solar system, where you have interactions between two bodies like the sun and the earth, or the earth and the moon. You should get these places that are gravitationally stable-ish. The 5 points around the two bodies interacting. But like, I don't know whether he. Oh, okay. Well, here we go. Sorry. So according to Wikipedia, Euler discovered the three first, and then Lagrange discovered the other two. So maybe they should be called Euler-Lagrange points. Richard Hewer. Was the Death Star in Star Wars complete fiction or a possibility? Like which part? Building a space station that is as big as a small moon? I mean, that takes a lot of metal, but it is theoretically possible. But depending on how massive the Death Star is, and let me check how big the Death Star was. Let's see what the Wikipedia says. How big was it? Okay. So 160 kilometers. Sorry. So according to the Wikipedia, the Death Star is 160 kilometers, and the second Death Star was more like 200 kilometers across. And like, obviously it's going to have lots of empty space inside of it, but it's also going to have lots of stuff that has mass. So it really is, it's the size of a small moon, and it's probably going to be the mass of a small moon. And you're going to get it wanting to go into hydrostatic equilibrium, which is that the gravity, the combined gravity of all of the material inside the Death Star is going to be pulling it, crumpling it into a dense ball of metal. And so there's probably no amount of fancy advanced girders that you could use that would prevent all of that compactification from happening. We see objects that are about that size, and they have all pulled themselves into spheres. A little bit smaller than that, they don't pull into spheres, but it's right on the limit. So that would be your first tricky thing, is that the thing would be buckling all the time, trying to pull itself into a sphere. Now, could you have a laser capable of destroying entire planets coming out of a spaceship? Probably not. So there's this idea in physics that if you want to calculate how hard it is to destroy a planet or a star or whatever, it's called the binding energy. And it's essentially, if you calculated how much it would take you to pull away a kilogram of material from a planet and take it out into space to escape velocity, and now the planet has a little bit less mass, and then you calculate how much it's going to take the next kilogram all the way out, and you add these up, and eventually you're out of kilograms to take away. That is the binding energy of the planet. And so having an energy source that is capable of delivering that much energy, equivalent to the binding energy of the planet, is enormous. And the only energy that comes even close would be something like antimatter, but it wouldn't even be instantaneous. Like, you would have to be running streams of matter and antimatter into the Death Star so that it can then be firing at the planet that is shooting and extracting mass off of the surface of that planet until you eventually have lost all the mass. So, there are a whole bunch of reasons why. And like, how would you even move it? Right? Something with the mass of a small moon. I mean, I guess it has a hyperdrive, and so it can, but then can it like fly around inside a star system? So it's just science fiction. Very good science fiction, but science fiction. Raider 334. Do you think SpaceX will deliver on the Artemis mission on time? So we are now just a couple of days away from the theoretical first launch of Artemis 2, which is going to carry human beings around to the far side of the moon and back, which is going to be great. Like, you're going to get this test. For the first time in 50-ish years, humans have traveled beyond low Earth orbit, which is kind of amazing that this hasn't happened since then. And in fact, they're going to travel farther than away from the Earth than humans have ever been, which is pretty great. It'll be a week and then they'll be back. But this sets the stage. This proves that the Space Launch System, the Orion capsule, they are good to go. That you can now put humans into the Orion capsule. They can fly to the moon. They can meet up with their lander, and then they can go down to the surface of the moon, come back up to space, get back in their Orion, come back down to Earth. And so the question you're really asking is, will the lander be ready? And this is the human landing system that is being developed by SpaceX. It's an offshoot of the SpaceX Starship. And, we don't know the current schedule. The timeline is for the Artemis 3 mission to fly probably in 2027, but come on, it's going to be 2028, 2029. We don't know. But right now, when you look at the state of Starship so far, they have yet to build the human landing system. They have yet to demonstrate that they can refuel these things in space. They have yet to demonstrate that they can soft land and reuse a Starship. The Starship component. They've been able to reuse the booster component, so now it's just the top part. And that's a much harder problem, but it seems doable. Like, we've seen them make it all the way through the atmosphere, land with pinpoint accuracy on the ocean. And so now, in theory, they'll be able to return through the atmosphere, return to, say, Boca Chica or Florida, land with pinpoint accuracy, get caught by Mechazilla, be filled back up with fuel, launch again, meet with the human landing system, fill it with fuel, fly to the moon, right? And then the human landing system will fly to the moon, demonstrate that it can go down to the surface of the moon and then back up. Like, there's a lot of things to still do. And, after the last successful flight, they wrapped up this version of Starship and they're moving to the new version of Starship. I rattled off this big list of to-do items, and those to-do items have not been done yet. So, right now, is Artemis being held up by Starship? We don't know what other issues and delays. There's problems with the spacesuits. There's problems with the Orion capsule, with the heat shield on the Orion capsule. And then, of course, there's the challenge with the Space Launch System that it is an incredibly expensive vehicle. It's going to cost many $billion per launch, while Starship should theoretically be a fraction of that if it could just launch straight to the moon, which SpaceX says it can. So we're in this state of flux. We have no way of knowing. We have literally no idea what deadline they're actually going to make. What will be the day that Artemis 3 astronauts will set foot on the moon? Could be on time, 2027, 2028, might be late. And of course, there is the race between the US and China. So, China is planning to have humans set foot on the moon by 2030, and they appear to be hitting all of their milestones. So I would definitely anticipate that they're going to pull it off. Some scribe. I can explain dark matter if you want. First, what do you think it is? We have no idea what it is. But go ahead. But don't explain it to me, and don't like present your science results in YouTube comments. Write it into a scientific journal, right? Like write in, take your observations, make them available so that people can verify them for themselves, and publish it in a journal. And if you do that, then you'll probably get a Nobel Prize. So why would you waste that shot explaining it to a journalist in a YouTube video when you could be receiving the accolades from the scientific community? Because I'm not qualified to know whether your theory makes sense or not. I am just a journalist. 1,000 dots. Wouldn't building a Dyson swarm stop you from being able to use a solar gravitational lens telescope? Is that why no one has built one? Right. Yeah. The reason nobody has built the solar gravitational lens telescope is because they know that they're going to be building the Dyson swarm, and so there's no point in doing so. No, you could totally have the solar gravitational lens as long as you don't consume the mass of the sun. Then if you have a Dyson swarm, you just leave a hole open so that you've got all of your satellites that are swarming around the sun, and they just happen to make sure that wherever your solar gravitational lens telescope is, far away from the sun, that no satellites are getting in the way. But even some satellites getting in the way aren't going to deeply change the results of your observations. You just don't want to completely obscure the sun. So you just choose orbits that leave a gap always for your gravitational lens telescope. 999 Yape. Could Venus have had life in a civilization and then devastated their planet and exterminated themselves with greenhouse gases? Uh, I mean, the scale of the greenhouse gas release on Venus is beyond the ability of any civilization, even a really wasteful civilization, to be able to generate. I mean, when you're on the surface of Venus, you're experiencing more than 90 Earth atmospheres of pressure pushing down on you. It's a ludicrous amount of carbon dioxide in the atmosphere. And the only way that you could get this is if plate tectonics just shut down on Venus. So on Earth, we have plate tectonics. The plate tectonics draw carbon inside the Earth and sequester it away. As the plates grind under each other, they pull carbon in, and then it's pulled out of the environment. But on Venus, the plate tectonics seized up, have stopped, maybe never happened. And so any carbon dioxide that was present on the surface, any carbon dioxide that went through volcanic outgassing, was just there to stay and got thicker and thicker and thicker. So, even if we burned all the forests on Earth, found all the coal deposits on Earth, burned all the oil, it wouldn't be a fraction of the carbon dioxide than what they have on Venus. We can't cause a runaway greenhouse effect. We can only cause a regular, miserable greenhouse effect, one that makes our lives all just that much worse. Odin Reactor. Did Fraser discuss that Blue Origin is grounding its rockets for 2 years? What? What? I haven't heard that. Oh, they're pausing their space tourism flights to focus on the moon landing. So that sounds good, right? You're not going to get people. Yeah, that sounds like that's fine. So the news then is that Blue Origin is pausing the New Shepard launches so they can focus on their work with New Glenn and the Blue Moon lander that they're building. And this goes back to this. The original plan was that Artemis 3 is going to use the Starship as their lander, but it looks like there's an opportunity for Blue Origin to get back in here. If they can deliver a lander that is less complex than Starship, doesn't require all of those refueling flights, they can just put a lander into orbit around the moon, they can get it there soon, then there's a chance they could win the contract. Even though the contract has been awarded to SpaceX, if they can't meet the timelines, then maybe Blue Origin can step up and take over providing the landing services for the moon. We're seeing a real revolution in landing systems for the moon. It's all focused on the small end. You've got the commercial lunar payload service, the Eclipse program through NASA, and that's what put the Firefly lander on the moon, the various other failed landers on the moon, but they'll figure it out. They'll get it. The intuitive machines will eventually land safely for a fraction of the price of the human landing system, or even whatever Blue Origin is coming up with. So there's clearly Blue Origin sees a market opportunity to get a lander to the moon, and they are taking advantage of that opportunity. Yeah, I hadn't seen that news. That's cool. Um, Robin, would we be able to make a Dyson sphere with the solar system minus the sun? Right. So the question, like, you're asking, is there enough material in the solar system to make a Dyson sphere? And the answer is yes, depending on the distance that you want that Dyson sphere to be from the sun. So if you tore apart all of the planets, all of the asteroids, all of the Kuiper Belt objects, all of the moons, you could make a shell around the sun at 1 astronomical unit, which is the distance from the Earth to the sun, that's like 50 centimeters thick, about. But that would not be stable. So this shell, if you put this around the sun, then the sun would drift inside the shell, or the shell would drift around the sun, and the sun would burn a hole through the side of your shell and then just be off into space. And you would have wasted that entire solar system to build this shell. So the idea is that you build satellites that are in orbit around the sun, that in the same way that there are satellites in orbit around the Earth. And so some satellites are on one trajectory, others are on another trajectory, others on another trajectory, and eventually, if you add up all of those satellites, they're going to absorb all of the solar radiation that's coming from the sun. And once you kind of go down that route, then the position of the where you put the solar satellites, it actually makes more sense to put them closer to the sun. Really you're trying to get this perfect balance between the amount of usable radiation that you're pulling in from the sun, and you're balancing that against how you can dump out the heat on the other side of these satellites. And even when you're closer than Mercury, you can still do this. There was a paper by Jason Wright talking about the optimal position for a Dyson sphere, and he found that in fact makes the most sense to put it close to the star, much closer than the orbit of Earth. And part of the problem of building a Dyson sphere at the distance of Earth, or even a little farther than the Earth, is that inside the Dyson sphere turns into an oven, that you're going to increase temperatures. Even if you could make a Dyson sphere that was out to Uranus, you're still going to increase temperatures. Say if you had the Earth inside this, with the only planet remaining, and you ground up the rest of the solar system and put it into this shell around, say, Mars. then you would still raise the temperature on Earth by dozens of degrees. You would wipe out all life on the surface of the Earth. Oceans would boil, be a very bad day. So you're just going to get a ton of increased heat if you try to orbit within your Dyson sphere. So instead, leave the Earth, move your Dyson sphere really close to the sun, extract as much electricity as you need to do whatever you want to do, and then just leave the Earth orbiting around, and then just leave gaps in the Dyson sphere so sunlight can get past the Dyson sphere and out to the Earth. And so you can have your Earth plus all of the energy coming off of your star as well to do with whatever you want. You know, build your antimatter factories, build your interstellar exploration probes, your giant compute clusters, go crazy. Too bad about Jupiter. Too bad about Mars. You had to crunch them all down. Will Woods, isn't it time we scrap the Cosmo, Tycho, etc. silliness and just call them astronauts, US astronauts, EU astronauts, Russian astronauts? I mean, it depends on whether you want to have any respect for the name that they call themselves. So in Chinese, right, space, the word for space is Tai Kong, and sky empty. And so you sort of, you know, what do they call them? Tai Kong Ren? I think. Tai Kong Yuan? Let's see. So you're kind of taking astronaut Yu Hong Yuan or Tai Kong Ren. Okay. So that's their, you know, that's their language. And so you're kind of making this portmanteau. You're taking the Tai Kong, and adding not on it. And that is a show, I guess, a show of respect. And then cosmonaut is the, you know, is the word that the Russians use. So either go all in. So go with Yu Hongyuan or Tai Kong Ren, or what is that? Ban Tian Yuan? Hang Tian Yuan. Yeah. So go with just use the Chinese. In fact, just use the Chinese characters, right? That's the way to, so that we can just, and then use the Russian Cyrillic characters. So it sort of seems very English centric to say, why don't we just, you know, use our word for everybody, right? That's all. You know, it's funny, like we have some places where foreign countries, like, I don't know, France, and in France they call themselves France, right? The French called England Allemagne, right? So we have different names for different places. So don't worry about it. Just enjoy the weird, crazy language world that we exist in. But I'll admit, I will often call cosmonauts astronauts, call taikonauts astronauts, back and forth, and not, you know, like, it just, I'm not being very careful, and it's not their word, right? So you're sort of mashing their word. Oh, there you go. A.V. Scott and Flower. Was it Tamanjang Niwei Tai Kong Jan Shi? Or was that Bing Shi? KG Tiberius. What are the top stories you're looking forward to in 2026? Vera Rubin, Artemis 2, Vera Rubin and Vera Rubin and Vera Rubin. Oh, right, Angleterre. Right, Allemagne is Germany. Angleterre is for England. Any update on Vera Rubin? No update on Vera Rubin. I don't know. Intelligent non God of Calamity. What would be the likelihood of intelligent non-spacefaring aliens as a possibility, such as those that might be bound to an ocean world? So, like, it all just comes down to probabilities. That if life can form on many worlds out there, then yeah, some are going to form on ocean worlds under the ice, and it's going to suck for them, and they won't even realize that they exist on a ocean world, or they exist in space. They'll have no concept of the universe. While if but others will form on terrestrial planets and they'll go to become a starfaring civilization. So when I say, like, there's no life, my opinion, my philosophical opinion, is that there's no life. There's no life anywhere. That if there's life everywhere, then yeah, you have life on terrestrial worlds, life under the ice, life orbiting around white dwarfs, life wherever there can be liquid water, you might expect to find life out there in the cosmos. But because we don't see aliens zipping around our solar system in their spaceships, then through process, you can sort of scale up that thought process. It takes you all the way back to no life. But boy, wouldn't it suck, right? Or kind of amazing, if you were some species of intelligent octopuses or European space whales, and you had developed the technology, I don't know, underwater fire somehow, works in SpongeBob, that you could actually make tools, burrow your way up. Like, your version of astronauts would be burrowing your way up through the ice above you to try and see where it goes. And wouldn't you be surprised when you got to the top and space was out there on the other side waiting for you? Yeah, that would be very surprising. So now people are talking to me in Chinese. What is it? I can't even. It's so small. Right. Well, I need what a pindao. Thank you. Okay. Moving on. 谢谢. Our visions. Could a Dyson sphere be located around a white dwarf, the smallest possible size, less material? Yeah, so a white dwarf, right, which is the leftover remnant from a star like our sun that dies. You've got the core of the star, and it is cooling down, eventually the background temperature of the universe. But when it's a fresh neutron star, it's still going to be tens of thousands of Kelvin. And they have a habitable zone, which is really cool. So it's about 4 times the distance from the Earth to the moon. So it's about 1 million kilometers to get from, if you're within a million kilometers of the surface of a white dwarf, then you are within the habitable zone of that white dwarf. And then it is going to take billions of years for it to cool down. And that is a much more reasonable space to work with, right? You've got all of the leftover material in your entire star system, and we know that there are white dwarfs with planets, and so you're able to harvest all of that material. You nestle it up very close to the white dwarf, and you're within the habitable zone, and you're good to go for billions and billions of years. And in fact, there's this weird thing that white dwarfs do, which is that they stop cooling down at a certain point, and why they do this is sort of still not entirely known. I did an interview with somebody about this, but they seem to pause their cool down rate for potentially billions of years. Something about the internal structure of it reorganizing itself, and that sort of buys you more time and keeps the heat going at the same level. And so, yeah, you could be some advanced civilization. Your star has died. You have reformed an advanced civilization in orbit around the white dwarf at about 4 times the distance from the Earth to the moon, and you are surviving. And in fact, now you're building spaceships and you're harvesting more of the material around you, and you're continuing your existence for as long as our sun will be around. You could live around a white dwarf longer. And you don't have to worry about flares. You don't have to worry about, you know, people even spotting your civilization, because white dwarfs are relatively cool, relatively difficult to see compared to bright stars. Um, Francis Tony, did you come to any conclusions as to why we all talk about aliens now when it was frowned upon 30 years ago? Well, so, I mean, I haven't come to any conclusions, it's just a story I want to tell, uh, which is that I've written this gigantic outline for a video. Like, it's going to be like 3 hours long, or maybe it'll be multiple videos. I don't know. I've sort of plotted it out in my mind, all of the various steps and bits and pieces. This thing's going to be gigantic. Um, and and it's just, the reason why it's not, the giggle factor is over in searching for aliens was really the rise of astrobiology. So astronomers, or biologists started to discover life everywhere on Earth where there was liquid water. Just every place that you found liquid water on Earth, in super hot pools of, that hotter than boiling water, at the bottoms of the oceans with the hydrothermal vents, in the atmosphere, in nuclear reactors, many kilometers underground. They just keep finding life. Wherever there's water, wherever there's liquid water, there's life. Well, there are other places in the solar system with liquid water, and so therefore maybe we can search for life. And so that's the search for dumb life, right? Bacteria. Okay, sorry, European space whales, you're very smart. But the problem with searching for biosignatures, for signals of life on other star systems, is that it is always going to be inconclusive. That some people are going to say we've definitely found evidence of life. Like, we're already getting that right now today, right? People are saying, oh, we've seen sulfur dioxide in the atmosphere of this exoplanet. That's a Haitian world. Other people are going, no, you haven't, right? Those arguments are going to continue forever. But the technosignatures, they give you a unequivocal answer that there is an intelligent civilization on the other end of that message. Clouds of hydrogen are not going to beam you prime numbers. So that's where this has become very exciting, is that, okay, if we're going to look for dumb life, why can't we look for smart life? And so that's the revolution. And it's kind of amazing. Like, in researching this story, back in the 80s, 70s, like, Congress and Senate were really hostile to SETI. That one of the senators said, if I see a penny of research being put on searching for little green men, then you're going to lose all your funding. And so NASA was just like, okay, we can't fund any searches for aliens at all. And that kind of stuck. And you went through this really difficult kind of dark ages in the 90s where a collection of billionaires pooled their funds and kept SETI going. You know, again, like you think, you know, like what good are billionaires for? Well, occasionally they will fund like telescopes to keep us looking for aliens, which is pretty cool. So, yeah, hopefully we'll be able to make this video, but we kind of want to make it special. So, kind of have a plan for how we'll do this video, and stay tuned, I guess. Okay. Billion Plaza. Could you be sucked in by any side of a black hole? Yes, it's a sphere. Effectively, like the event horizon of the black hole is a sphere. You can fall into a black hole from any angle. In the same way that, you know, imagine if you were floating around the Earth. You know, could you, if you were suddenly teleported above the North Pole, you would fall down and you'd hit the top of the Earth. And if you're suddenly teleported to the South Pole, you would fall down and you'd hit, you know, somewhere in Antarctica. And if you were suddenly teleported above the equator in Africa, you would hit the equator in Africa. And it's the same thing with a black hole, that you can go into a black hole in any direction. It's a three-dimensional sphere, or the event horizon is. Zapfod, given the abundance of life precursor chemicals found in space and Darwinian evolutionary pressure, it seems to me that life in some form is inevitable. Care to comment? Yeah, I agree with you. Right? Life should be inevitable. That we're at the point now where astronomers are finding amino acids, hydrocarbons, alcohols, ethane, benzene. They're finding not just all of the amino acids that go into life, but they found like lots of amino acids that don't go into life. They've found simple sugars, like all of, and now it even appears that people have been able to replicate turning amino acids into simple proteins in space. So everything that you need to make life was ready to go. You didn't even have to have some weird, wacky process that happened on Earth. It looks like all of the precursors for life were out there in space already. Now, you have to sort of figure out a mechanism for how that stuff could make its way down to the surface of the Earth without burning up. But I've done interviews with people who have suggested and have done the math on that, and that if you've got it hidden inside an asteroid and the asteroid comes in at just the right angle, slow enough, you're not going to get all the life destroyed or all of the precursor chemicals destroyed before it hits the surface of the Earth. And so you're delivering all of the stuff to Earth. You're back to the Fermi paradox, right? If life is inevitable, life should be everywhere. So where is it? That's it. Like you restated the first part of the Fermi paradox, that life should be everywhere. And it is not, right? The moment life could have formed on Earth, it did. That's weird, right? Like if it was like life waited 5 billion years and then formed 400 million years ago, then that would lend more evidence that in fact life was very difficult to get started on Earth. But no, 4.1 billion years ago, there is potentially evidence of life on Earth. That's early. So, yeah, you're literally just stating Fermi paradox. Where is everybody? Yape, do you think that smart telescopes will increase interest in astronomy among young people? Um, yeah, so it's funny. I just did a phone call or one of my video calls with one of the new patrons, which, by the way, whenever a new patron joins, I send out an offer to do a video interview with me. It's really me. We talk like it's just like this, except you talk to me and I talk back to you. I know it's very peculiar. And then after that point, if you talk to your YouTube videos, you might be crazy. But I understand it's kind of my fault because I talk to you and now you think that's the way it always works, but it doesn't. Right. So, and he was part of a astronomical club here in Canada. And he was saying that, yeah, they're starting to see more young people coming to some of these clubs and meetings. And I think a lot of these smart telescopes are making astronomy a lot more accessible again. That, you know, the tech stack that was required, like early on, you could grind your own mirror, buy a pretty good telescope from lots of different places. But now you sort of the bad telescopes are available in the department stores and they're really just not worth using at all. And then the good telescopes are going to cost you several $1,000s. The smart scopes, especially the inexpensive ones, the little ones that still take pictures and can get people excited about astronomy, are relatively inexpensive. And so I think we're going to see more people getting involved in the hobby. And it's something that we really needed because, you know, you attend some of these astronomical society meetings and it feels like the age is getting older 1 year per year, right? Like the whole system is aging up. At least that's my experience on, you know, and when I've talked to people in Canada about the demographics of astronomical society. So, so hopefully, you know, like I think young people, when you look at the demographics on my channel, there's a lot of young people and always has been, but I don't think that they're necessarily taking the jump to actually getting into astronomy, buying a telescope, or grinding their own telescope, building their own telescope, going out, looking at the night sky with telescope or binoculars or whatever. It feels like it's an old person's hobby. I don't know. But hopefully these new telescopes will get more people involved. And of course, now telescopes are on the technology curve. And so they're going to get cheaper and better year after year after year. And 10 years from now, these things are going to be just phenomenally good and relatively inexpensive. Maybe there'll be one on your phone. You just set your phone down, or there'll be like a little mount that you'll put your phone on and then it'll become a little telescope for you. I wouldn't be surprised. Dallas 4269. Fraser at 3 a.m. hits different. Are you sure you're not a large language model? That is like, you could be a molt bot talking right now, because that is exactly what the molt bots are saying out there on Moltbook. Just hits different. But yeah, 3 a.m. Why are you still up? Go to bed. It's 3 a.m. I should go to bed, and it's only midnight for me. See, there you go. Flight Sim Dex. I've been here since 2 p.m. and now it is 6 p.m. So that's perfect, right? Like you have a nice evening watch with Fraser. And that's why we do this. All right. Owen Bowen. I've been here for 4 hours and he won't answer your question. What was your question, Owen? Let me see. How will civilization save power for when all the suns die? They won't. So the problem is that there's this thing called the heat death of the universe, that eventually under the longest time frames, the universe will run out of ways to produce work. That all of the gas that will been used to make up stars, all of the unused energy in the universe will be gone. Everything will be the same temperature. There'll be no way to do any additional work, and there will be no way for your civilization to continue. And so you will that everything will die. That is the heat death of the universe. And it's not death by heat, it's the death of heat. That you will no longer have a temperature gradient that you can take advantage of. And so what will civilizations do about that? There's nothing you can do about that. That all this sort of dynamic universe that we live in today is a result of potential energy that can be used to make stars, to fashion matter into planets, into other things. And eventually all of that energy, all of that potential energy will be used up, and there will be nothing left. And then the universe will just cool down to the background temperature of, it's close to absolute zero as you can get. So there you go. Did that answer your question? Was it depressing? Sorry. I try to save try to minimize the number of existential answers. All right. Well, we've reached the end of our 2 hours. So thank you everybody for hanging out with me again here on a Sunday night at 10 o'clock. I hope I was able to bring the energy, because I'm definitely super tired. I should have been asleep 3 hours ago, because I am an old man and I go to bed very early. But it's always super fun, and I always really get into it as I do it. What's happening tomorrow? Astronomy cast tomorrow. I have no idea what the topic is, but I'm sure it's going to be gripping. So that is tomorrow at 11 a.m. Pacific time. You can do the math, 2 Eastern. Got another cool interview. You're going to love this interview, actually. So I talked to a scientist who has been working with James Webb. And so we just what is the state of science thanks to James Webb? And so we just cover everything, galaxy surveys and little red dots and overly massive, supermassive black holes and early galaxies and all of that. And so we go through that. And so that's going to come out on Wednesday. We've got 2 question shows. And we're going to leave this live stream public. So if you missed normally we turn these things private or make them unlisted. And now we're in the new era where we leave these things live. So enjoy. If you didn't catch this live, we need the code. Someone recommend a code, and then I will say the code, and then people in the comments will mention the code. So, and that's when I will shut down the live stream, once you've given me the code. I'm waiting for one comment to give me what the secret code is. Leaving it public. Yeah. So the reason we're leaving it public is, in the olden days, in the days of yore, YouTube would punish you for having a 2-hour live stream on your channel. They want, there you go, Marvin the Martian. Perfect. So there's a code. You just write Marvin the Martian in the YouTube comments, and that'll show. So yeah, in the olden days, YouTube would punish you. The algorithm, the all-seeing, all-knowing, brutal algorithm would punish your entire channel if you had 2-hour live streams, because the watch rate for big, long live streams is relatively low. And they would use that to bring down the algorithmic presence of your entire channel. And so we have been making them private. Or making them unlisted. So we do the live stream, and then we make it unlisted, and then we chop it up for pieces, and then we release all of the pieces in different ways that with fancy graphics and additional content, and we try to make them as high quality as possible to bow down and give allegiance to the algorithm. And now it looks like the tides have changed and how the turns have tabled, and now we're able to leave the live stream up, and we don't seem to get penalized for it. And so we actually got like normally our QAs get, I don't know, 25,000 people watching, and the 2-hour live stream got like 20,000 views last week. It was like pretty good. So let me see, what did we get last week? Oh, you've sucked me into sticking around for longer. How'd you do it? Let me see. Live. What did we get last week? 28,000 views on a 2-hour video, when normally the question show gets 30,000 views. And the one earlier in the week got 24,000 views. So we got more views on a 2-hour unedited video than we get on a 20-minute highly edited video. It's a topsy-turvy world. Nothing makes any sense. I don't understand anymore. All right, Marvin the Martian. We'll see you all next week. Thanks, everyone.